There is something at the centre of our galaxy that should not exist. It has the mass of 4 million suns. It controls the orbit of every single star in the Milky Way. It has been studied for decades, photographed with a telescope the size of an entire planet, and celebrated with a Nobel Prize. Scientists have staked their careers on what it is, and they may have been wrong for 50 years. We called it a black hole. A wound in space-time so deep, so absolute, that not even light escapes its grip. We were certain, beautifully, dangerously certain, but certainty in the universe is a fragile thing. In February 2026, a team of physicists published something extraordinary, something that quietly cracked the foundation of one of astronomy's most celebrated discoveries. Their mathematics showed with less than 1% margin of error that the monster at the heart of our galaxy could be something far stranger than a black hole. Something invisible. Something that fills the entire universe, yet has never once been directly detected. Dark matter. The same mysterious substance that makes up 85% of all matter in existence. The invisible architect of galaxies, of cosmic structure, of reality itself. And if these scientists are right, it has been hiding in the most obvious place imaginable, right at the centre of our own galaxy, disguised as something else entirely, while we looked directly at it and never once suspected the truth. What you are about to discover does not just challenge our understanding of one object in one galaxy. It pulls at the thread that holds our entire picture of the universe together. Two of the deepest mysteries in all of modern physics, the nature of supermassive black holes and the identity of dark matter, may not be separate puzzles at all. They may be the same puzzle, and the answer has been sitting 27,000 light-years away, patient as eternity, waiting for us to finally ask the right question. If questions like this keep you awake at night, if the mystery of the cosmos pulls at something deep inside you, hit subscribe and join a community that lives for exactly this kind of discovery, because what comes next will change the way you see the night sky. Forever, we begin. There is a place in the universe where everything ends and everything begins. Not at the edge of the cosmos, not at the boundary of some distant, unreachable galaxy, billions of light years away, but here, right here, at the centre of the very galaxy you call home, 27,000 light years from the pale blue dot where you were born, where you learnt to speak, where you first looked up at the night sky and felt that quiet electric pull of something enormous and unknowable pressing down on you from above. That feeling was not your imagination. That pull is real, and it has a name. Sagittarius A star. Say it slowly. Let it sit in the air for a moment. Because this is not just a name. It is the designation we have given to the most massive, most compact, most gravitationally dominant object in the entire Milky Way. An object so powerful that every single star in our galaxy, all 400 billion of them, traces its slow, sweeping orbit around it, the way water circles a drain. Including our own sun. Our sun, which is so large that 1 million Earths could fit comfortably inside it, orbits Sagittarius A star like a speck of dust caught in a slow, silent whirlpool. It takes our sun more than 200 million years to complete a single orbit. 200 million years. The last time our sun was in this exact position in the galaxy, dinosaurs did not yet exist on Earth, and at the centre of that whirlpool that is where we are going. Sagittarius A star sits at the very heart of the Milky Way, buried beneath 30,000 light-years of stars, gas, and dense interstellar dust so thick that no visible light can pass through it. You cannot see it with your eyes, you cannot photograph it with an ordinary camera. For most of human history, We did not even know it was there. It hides in plain sight, cloaked by the galaxy itself, like a secret kept at the bottom of the deepest ocean present, always present, but invisible to anyone who does not know exactly how to look. What we do know about it stretches the imagination to its very limits. Sagittarius A star has a mass of approximately 4.3 million times the mass of our Sun. Read that again, slowly. 4.3 million suns. All of that mass is compressed into a region of space so small that it could fit entirely within the orbit of Venus. The distance from the Sun to Venus, a distance we humans once thought was the entire scope of all existence, is roughly 108 million kilometers. The entire mass of 4.3 million suns is squeezed into a space smaller than that. Smaller than the gap between two neighbouring planets in our own backyard. The density implied by those numbers is almost impossible to think about. It is the kind of density where the normal rules of matter, the rules that keep chairs solid and stars burning and atoms from collapsing into themselves, begin to break down. It is a density that sits at the very edge of what our equations can describe. For decades there has been one explanation that fits all of this. One neat, elegant, terrifying explanation that the scientific community has rallied around with remarkable confidence. A supermassive black hole. A point in space where gravity has won completely. Where matter has collapsed so thoroughly that it has punched a hole through the fabric of space-time itself. A place where the escape velocity, the speed you would need to reach to break free of its gravitational pull, exceeds the speed of light. Where not even light, the fastest thing in the universe, can outrun it. Beyond a certain boundary, called the event horizon, everything that falls in stays in. Forever, it is the universe's most dramatic statement. A full stop, written in the language of gravity. And for a long time this explanation seemed not just likely, but almost certain. The evidence was strong, the mathematics was consistent, the observations pointed in one direction, and that direction was black hole. So we built the consensus. We accepted it. We awarded Nobel Prizes on the strength of it. We pointed a telescope the size of the entire Earth at the galactic centre and captured what we called its shadow. We gave it a name, we made it familiar. But familiarity is a dangerous thing in science. Because familiarity can make us stop asking questions. It can make us mistake a very strong case for a closed case. And in the universe in this vast, strange, endlessly surprising universe closed cases have a habit of creaking open again. Here is something important to hold on to as we travel deeper into this story together. The Nobel Prize citation awarded in 2020 for the discovery at the centre of our galaxy did not say black hole. Not exactly. The official language was careful and deliberate. It said, the discovery of a supermassive compact object at the centre of our galaxy. A compact object, not a black hole. The scientists who won that prize are among the most rigorous, most careful researchers in the world, and they chose those words on purpose. Because while the consensus says black hole, the proof has never fully arrived. That distinction between consensus and proof is where our journey truly begins. Because in February of 2026, a team of researchers published a paper that took that distinction seriously. A paper that asked, quietly and precisely, whether something else entirely might be sitting at the centre of the Milky Way. Not a black hole, not a collapsed star, but a dense, stable, ancient core of something we have been searching for across the entire universe for nearly a century. Dark matter. The same invisible, undetected, gravitationally dominant substance that makes up roughly 85% of all the matter in the cosmos. The substance that holds galaxies together, that shapes the large-scale structure of the universe, that our most sensitive instruments have never once directly touched or measured or confirmed. What if it has been here all along? Not scattered across the fringes of the galaxy in some diffuse, invisible cloud, but concentrated, compressed, present right here at the very centre of everything. What if the beast at the heart of the Milky Way is not a wound in space-time, but a structure built from the universe's most mysterious material? This is not a fringe idea anymore. It is a mathematically precise, observationally tested hypothesis that has been published in one of the most respected journals in astrophysics. It cannot reproduce the observations any less accurately than the black hole model. And that alone is enough to demand that we look more carefully, that we slow down, that we ask the question we perhaps should have been asking all along: what exactly is Sagittarius A star? The answer, as we are about to discover, may change the way we understand not just the centre of our galaxy, but the nature of the universe itself. It connects two of the deepest mysteries in all of modern physics. It challenges some of our most confident assumptions. And it begins, as so many of the best scientific stories do, not with a breakthrough, but with a signal. A faint, strange, unexpected radio signal detected almost by accident nearly a century ago. The year was 1931. The world was a different place. No computers, no satellites, no spacecraft had ever left the ground. Television was a novelty. Radio was still magic to most people. And a young engineer named Carl Jansky was standing in a field in New Jersey trying to solve a very practical problem. Static. Radio static. The kind of crackling, hissing interference that interrupted telephone calls transmitted over radio waves. The Bell Telephone Company wanted to understand where this noise came from. Lightning, they suspected. Thunderstorms, local electrical interference. Jansky's job was to find it, identify it, and figure out how to filter it out. So he built an antenna, a strange-looking thing, a rotating framework of brass pipes and wooden beams mounted on old Ford Model T wheels so it could turn in a slow circle. He pointed it at the sky and listened. And what he heard changed everything. There was static from thunderstorms, yes, there was interference from nearby electrical equipment. But there was also something else, a faint, persistent hiss that rose and fell with a rhythm Jansky could not explain. It peaked once every 23 hours and 56 minutes, not 24 hours, not the rhythm of the Earth's rotation relative to the Sun, but the rhythm of the Earth's rotation relative to the stars. The signal was coming from space. Jansky tracked it carefully, patiently, over weeks and months. The hiss seemed to come from the direction of the constellation Sagittarius. The Archer. The Centaur. The ancient pattern of stars that from Earth appears to point directly toward the centre of the Milky Way. He published his findings. And the world barely noticed. Astronomers at the time were occupied with visible light, with stars and nebulae and planets they could actually see through telescopes. Radio waves from space were strange, unexpected, and difficult to interpret. What could possibly be generating them? Jansky himself speculated it might be stars, or clouds of ionized gas, or perhaps something entirely unknown. He did not have the tools or the funding to investigate further. The mystery hung in the air, unresolved, like a question asked into a void. For years almost no one followed up on Jansky's discovery. The field of radio astronomy did not truly exist yet. There were no textbooks, no graduate programs, no instruments designed specifically for the task. Only a handful of curious minds scattered across the world, listening to the whispers of the universe in frequencies human eyes could never perceive. It would take decades before the picture began to come into focus. After the Second World War, radio technology advanced rapidly. Radar systems developed during the conflict were repurposed for scientific research. Astronomers began building radio telescopes, large dishes designed to collect and focus faint radio waves from the cosmos the same way optical telescopes collect light. And when they pointed these new instruments toward the center of the galaxy, they heard the signal again. Louder now. Clearer. There was something there, something bright in radio frequencies, something compact, something powerful. But what? In those early decades, black holes were still considered purely theoretical. They existed only as mathematical solutions to Einstein's equations of general relativity, strange, exotic predictions that most physicists assumed did not actually exist in nature. The idea that matter could collapse so completely that it would trap even light seemed too extreme, too abstract, too far removed from reality. So scientists proposed other ideas. Perhaps the signal came from a dense cluster of stars crowded together at the galactic center, their combined light and motion generating the radio glow. Perhaps it was the remnant of a massive supernova explosion, still radiating energy thousands of years after the blast. Perhaps it was multiple objects, overlapping and blending together in a confusing tangle. The debates buzzed through the scientific community like static on a poorly tuned radio. Theories rose and fell. Observations improved, but slowly. The galactic center was obscured by so much dust and gas that optical telescopes could not see through it at all. Only radio waves and, later, infrared light could pierce the veil. Then, in 1974, two astronomers named Bruce Ballack and Robert L. Brown used the newly completed Very Large Array in New Mexico to observe the galactic center with unprecedented precision. And they found something remarkable. The radio signal was not diffuse. It was not spread out across a wide region. It came from a single, compact source. An object. A specific, localized point in space sitting right at the dynamical center of the galaxy. The place where, according to the motion of surrounding stars and gas, the strongest gravitational pull seemed to be concentrated. Robert Brown gave it a name. Sagittarius A star. The brightest radio source in the Sagittarius constellation. The asterisk, the star symbol, was added to indicate something special, something extraordinary, a marker of significance. By the time Sagittarius A star received its name, the theoretical landscape had shifted. Physicists had spent the intervening decades exploring the mathematics of black holes. Roger Penrose had proven, rigorously and elegantly, that black holes were not just possible but inevitable under certain conditions. They were a direct consequence of Einstein's theory of relativity. If enough mass gathered in a small enough space, collapse into a black hole was not just likely, it was unavoidable. The pieces began to fit together. A compact object, millions of times the mass of the Sun, sitting at the gravitational center of the galaxy, emitting intense radio waves from the swirling, superheated matter falling toward it. It looked like a black hole. It behaved like a black hole. And very quickly the scientific consensus began to form around that conclusion. But here is the thing about consensus. It is built on probability, not certainty. It is the position that seems most reasonable given the available evidence. But it is not the same as proof. And in the case of Sagittarius A star, the available evidence was still indirect, still incomplete, still filtered through layers of dust and distance and mathematical interpretation. No one had seen Sagittarius A star directly. No one could. By definition, if it truly was a black hole, it would emit no light of its own. Its presence could only be inferred, only felt through its gravitational influence on everything around it. And that influence was extraordinary. As radio telescopes gave way to infrared observatories capable of peering through the galactic dust, astronomers began to detect something even more stunning than the central object itself. They began to see stars, individual stars, orbiting the dark centre at speeds that defied comprehension. Stars moving so fast that their motion could be tracked not over centuries, but over years, over months, over weeks. These stars became the key. They became the messengers, the witnesses, the evidence that would eventually earn 2 research teams a Nobel Prize and open the door, just slightly, to the possibility that everything we thought we knew about the galactic centre might be incomplete. Because to understand what Sagittarius A star truly is, we must first understand the stars that dance around it. Stars that move faster than almost anything else in the known galaxy. Stars that should not, by any ordinary logic, be able to exist where they are at all. Stars that even now are whispering secrets we are only just beginning to hear. Imagine you are watching a river. A wide, calm river flowing slowly past you. You can see leaves floating on the surface, drifting lazily downstream. You can predict where they will be in an hour, in a day. Their motion is gentle, predictable, ordinary. Now imagine one of those leaves suddenly accelerates to the speed of a bullet train. It tears across the water's surface, looping in tight circles, whipping around an invisible centre point, then racing back the way it came. Over and over. Year after year, never slowing, never stopping. You would know immediately that something extraordinary was happening, something powerful, something hidden beneath the surface. That is what astronomers saw when they finally got a clear look at the stars closest to Sagittarius A star. By the 1990s, infrared technology had advanced enough to peer through the thick curtain of dust that hides the galactic centre from our view. Infrared light has longer wavelengths than visible light. It can pass through dust clouds that would completely block ordinary starlight. And when astronomers pointed these new infrared telescopes towards Sagittarius, they did not just detect the faint radio source at the centre. They saw stars, dozens of them, bright, hot, young stars clustered in a region where, by all logic, stars should not exist at all, and those stars were moving. Fast, impossibly fast. They called them S-stars. The S stands for source, a technical term from the catalogue systems astronomers use, but you can think of the S as standing for something else. Speed, because these stars move faster than almost anything else we have ever observed in our galaxy. The fastest among them reach velocities of 24,000 kilometers per second. Let that number settle for a moment. 24,000 kilometers every single second. That is roughly 8% of the speed of light. 8% of the fastest speed the universe allows. For a star and object millions of times more massive than anything humans have ever built to move that fast, requires gravitational forces of unimaginable strength. One star in particular became the focus of intense study. Its name is S2, also called S02 in some catalogues. It is a hot blue star about 15 times the mass of our Sun, and it orbits Sagittarius A star in a tight, elongated ellipse that brings it terrifyingly close to the centre. S2 completes one full orbit in just under 16 years. 16 years. A human lifetime can contain 5 or 6 of S2's years. A child born when S2 was at one point in its orbit will have learnt to drive a car, graduated from school, and started a career by the time it returns to that same position. Astronomically speaking, that is almost instantaneous. It is the blink of an eye. And it gave astronomers something they rarely get when studying the cosmos. Real-time data. Starting in the early 1990s, 2 independent research teams began tracking S2 and the other S-stars with obsessive precision. One team was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany. The other was led by Andrea Ghez at the University of California, Los Angeles. Both teams used some of the most powerful telescopes on Earth. Both teams worked for decades, image by image, measurement by measurement, building a detailed map of how these stars move. And what they found was stunning. The stars were not drifting randomly. They were not wandering. They were orbiting. Each one followed a precise, predictable path determined entirely by gravity. And all of those paths pointed to the same conclusion. There was something at the centre, something with enormous mass, something compact, something that exerted a gravitational pull strong enough to whip stars around like stones on a string. By carefully measuring the speed and shape of S2's orbit, the teams could calculate exactly how much mass was pulling on it. The math is rooted in the same principles Isaac Newton used to understand the Moon's orbit around Earth, refined and extended by Einstein's theory of relativity. When you know how fast something is moving and how tightly it is orbiting, you can work backwards to determine the mass of the object it is orbiting around. The answer came back with startling precision: 4.3 million times the mass of the Sun. And that mass was confined to a region no larger than 23 to 25 million kilometres across. Small enough to fit comfortably inside the orbit of Venus. Small enough that if you could somehow stand at the edge of it, the entire structure would fit within the span of a single planetary system. That combination, enormous mass, tiny size, left very few possibilities. In fact, it left almost no possibilities at all. According to every model, every equation, every simulation astronomers could run, there was only one type of object that could be that massive and that compact. A supermassive black hole. The evidence was so strong, so compelling, so thoroughly documented over decades of observation, that in 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics. They shared it with Roger Penrose, a mathematician who had proven decades earlier that black holes were not just theoretical curiosities, but real, inevitable consequences of Einstein's equations. The Nobel Committee's citation was careful. It honoured them for the discovery of a supermassive compact object at the centre of our galaxy, not explicitly a black hole. But the implication was clear. The consensus was solid. The case was as close to closed as science ever allows. And yet, there was something else moving near Sagittarius A star. Something stranger than the S stars. Something that did not quite fit the familiar categories. Astronomers called them G objects. The G stands for gas, but that name is misleading. Because these objects behave like stars moving in predictable orbits, glowing faintly in infrared light but they look like clouds. Diffuse, stretched, shapeless, the first G object was discovered in the early 2000s. As it approached Sagittarius A star, it began to change, its shape distorted, it elongated. It stretched like taffy being pulled, deforming under the crushing grip of gravity. But it did not tear apart. It did not evaporate. It survived its closest approach and continued on its orbit, gradually reforming as it moved away again. No one is entirely sure what G-objects are. The leading idea is that they might be stars wrapped in thick cocoons of gas and dust, or perhaps they are clouds of material in the process of collapsing to form a star. Or maybe they are something else entirely, something unique to the extreme environment near the galactic centre. What matters for our story is this. Any model that tries to explain what Sagittarius A star truly is must also explain the G objects. It must reproduce their orbits. It must account for their strange stretching and reshaping. It must fit the data not just for S2, but for all the objects dancing in that violent, invisible gravitational field. For years, the supermassive black hole model did exactly that. It fit the observations beautifully. Perfectly, it explained the speeds, the orbits, the distortions. It left no room for doubt. But in February of 2026, a physicist named Valentina Cresby and her team published something extraordinary. They took a completely different Model 1 that had been quietly sitting in the background of scientific literature for decades and tested it against the same data. The S stars, the G objects, the orbits, the speeds, everything, and their model worked just as well. Not almost as well, not approximately, but precisely. To within less than 1% difference. Indistinguishable given the limits of current observations. Their model did not require a black hole at all. It required something else. Something invisible. Something we have been searching for across the entire universe for nearly 100 years. And suddenly, the question was no longer whether Sagittarius A star is a black hole. The question became, how can we tell the difference? There is a moment in science when the work is done. When the data has been gathered, the calculations checked and rechecked, the papers written and peer-reviewed. When the results are announced not in whispers, but in headlines. When the world's most prestigious institutions gather to say, yes, this is true, this is important, this changes what we know. That moment came for Reinhard Genzel and Andrea Ghez in October of 2020. The Nobel Prize in Physics. The highest honour in science. The recognition that comes once in a lifetime, if at all. It was awarded to them for decades of patient, meticulous, breathtaking work, for tracking the motion of stars around Sagittarius A star with such precision that they could weigh the invisible object at the centre, for proving that something massive and compact sits at the heart of our galaxy. They shared the prize with Roger Penrose, the British mathematician, who in 1965 proved that black holes are not just mathematical curiosities. They are real, physical predictions of Einstein's general theory of relativity. Penrose showed that when enough mass collapses into a small enough space, the formation of a black hole is unavoidable. Inevitable, written into the fabric of the universe itself. Together, the three laureates represented both sides of the story. Theory and observation. Mathematics and measurement, the prediction and the evidence. And the evidence was extraordinary. Over more than 2 decades, Genzel's team in Germany and Gez's team in California independently tracked the orbits of stars near the galactic centre. They used adaptive optics, a technology that compensates for the blurring effects of Earth's atmosphere in real time. They captured thousands of images. They measured positions down to incredible precision, tracking stars as they moved across the sky in paths no larger than the width of a human hair held at arm's length. From those measurements, they calculated the mass of the object pulling on those stars, and the number they arrived at was consistent, reproducible, and undeniable. 4.3 million solar masses. That is the mass of 4,300,000 suns, all concentrated in one place. To put that in perspective, if you replaced our Sun with Sagittarius A star, its boundary would stretch from the Sun's current position nearly to the orbit of Venus. Everything inside that orbit Mercury, and much of the space between, would be swallowed by its gravitational reach. But here is what makes that number so astonishing. The mass is not spread out. It is not diffuse. It is packed into a region only 23.5 to 25 million kilometers across. That is roughly 1/6 the distance from the Earth to the Sun. Compressed into that impossibly small volume is more mass than exists in 4 million star systems like ours. The density implied by those numbers is staggering. It exceeds anything we encounter in normal matter. It exceeds the density inside neutron stars, the collapsed cores of dead suns where a teaspoon of material weighs as much as a mountain. At the scale of Sagittarius A star, the equations of normal physics begin to break down. Space and time themselves begin to warp. And according to general relativity, there is only one stable configuration that can sustain such extreme density. A black hole. The case seemed airtight. The observations fit. The mathematics agreed. The consensus solidified. Genzel and Ghez received their Nobel Prize. Press releases called Sagittarius A star a supermassive black hole. Textbooks were updated. The story felt complete. But if you read the official Nobel Prize citation carefully, you will notice something. It does not say black hole. The exact wording is this: for the discovery of a supermassive compact object at the centre of our galaxy. A compact object, not a black hole. The language is deliberate. Precise, scientific. Why? Because despite the overwhelming evidence, despite the decades of work, despite the consensus among nearly every astronomer working in the field, Sagittarius A star has not been proven to be a black hole. Not definitively. Not beyond all doubt. This is not a flaw in the science, it is a feature of it. Science does not deal in absolute certainty. It deals in probabilities, in models, in the best explanation given the available evidence. And the black hole model is, without question, the best explanation we have. It fits the data beautifully. It is supported by theory. It has withstood every test thrown at it. But best explanation is not the same as only explanation. By definition, we cannot observe a black hole directly. A black hole emits no light. It has an event horizon, a boundary, beyond which nothing, not even light, can escape. Everything that crosses that line is lost to us forever. We cannot see it. We cannot touch it. We cannot measure it with instruments. All we can do is observe its effects. The way it pulls on nearby stars, the way it bends light, the way matter heats up and glows as it spirals inward. We infer the black hole's existence from those effects, the same way you might infer the presence of wind by watching leaves move, and that inference, strong as it is, leaves a gap, a narrow space where other possibilities can still exist. Some of those possibilities have been ruled out. In the early days, scientists wondered if Sagittarius A star might be a dense cluster of stars, thousands of stars packed so tightly together that they appeared as a single object. But the data eliminated that idea. A star cluster that dense would tear itself apart. The stars would collide, merge, or fling each other out into space. It could not remain stable. Other ideas were proposed and discarded. A single supermassive star, the remnant of an ancient supernova. None of them fit, but a few alternatives remain. Faint, speculative, sitting quietly in the scientific literature. Boson stars, theoretical objects made of exotic particles. Gravi stars, shells of high-energy matter surrounding dense cores. And dark matter cores compact objects made entirely of the invisible substance that holds galaxies together. For years these ideas existed on the fringes. Interesting, perhaps, but not necessary. The black hole model worked so well that there seemed no reason to pursue them seriously. Until 2026. That was when Valentina Crespi and her collaborators published their results. They tested a dark matter core model against the same data Genzel and Ghez had used. The same stars, the same orbits, the same measurements. And the dark matter model reproduced the observations with less than 1% difference from the black hole model. Less than 1%. Within the margin of error. Indistinguishable, given the precision of current instruments. That does not mean the black hole model is wrong. It does not overturn decades of careful work. But it does mean something profoundly important. It means we do not yet know for certain what Sagittarius A star truly is. We know it is massive. We know it is compact. We know it warps space and bends light and controls the motion of everything around it. But whether it is a black hole with an event horizon and a singularity at its core, or whether it is something else, something made of dark matter, something without a singular point of infinite density, that question remains open. And the answer to that question does not just tell us about one object at the centre of one galaxy, it connects to something much larger. Much deeper, because if Sagittarius A star is made of dark matter, it could solve two mysteries at once. The nature of the galactic centre, and the nature of dark matter itself. The substance that makes up most of the universe. The substance we have never seen. The substance we have been searching for, unsuccessfully, for nearly 100 years. What if it has been here all along, right at the heart of everything, waiting? On May 12, 2022, the world saw something it had never seen before. Not with human eyes, not directly. But through the combined power of 8 radio telescopes scattered across the planet from Hawaii to Chile. From Arizona to Antarctica, synchronized with atomic clocks and stitched together by supercomputers into a single virtual instrument the size of the entire Earth. The Event Horizon Telescope. A collaboration involving more than 300 scientists from 80 institutions across 20 countries and regions. Years of planning. Petabytes of data. Algorithms designed specifically to turn radio waves into images, all of it focused on one target. Sagittarius A star. And when the image was finally released, it spread across every major news outlet within hours. A glowing orange ring against a black background, fuzzy, blurred slightly, but unmistakable. Beautiful in a strange, almost haunting way. The headlines called it the first direct image of our galaxy's black hole, the first photograph of the shadow at the centre of the Milky Way, proof, finally, that Sagittarius A star is what we have long believed it to be. But here, once again, we must slow down. We must look carefully at the words, at what the image truly shows, and at what it does not. Because this image, as stunning as it is not a photograph in the ordinary sense. You are not looking at Sagittarius A star itself. You cannot. If it is a black hole, it emits no light. By definition, it is invisible. What you are seeing instead is everything around it. The glow comes from superheated matter. Gas and dust spiraling inward at nearly the speed of light, compressed and accelerated by gravity so extreme that friction heats the material to billions of degrees. At those temperatures, the matter radiates across the electromagnetic spectrum X-rays, ultraviolet light, and crucially for the Event Horizon Telescope, radio waves. Those radio waves trace a ring, a bright, uneven circle surrounding a dark center. The ring exists because even light bent and twisted by gravity still follows rules. Photons emitted from the swirling matter curve around the central object. Some escape outward toward us. Others spiral inward and are lost. The boundary between those two fates creates the appearance of a ring. And inside that ring is darkness. That darkness is what the media called a shadow. And in one sense, they are right. It is a shadow, a region where no light reaches us, because the gravity is so strong that it bends all nearby light away. But calling it a shadow of a black hole is where the language becomes slippery. Because what creates a shadow? The object itself, yes, but also the light source behind it. The glowing matter. The angle of observation, the way space-time is curved in that region. All of these together produce the image we see. And here is the critical point. That shadow does not require a black hole. It requires extreme gravity. It requires mass concentrated in a very small space. It requires space-time to be warped dramatically. But those conditions can in principle be met by other objects too. In 2024, 2 years after the Event Horizon Telescope image was published, a physicist named Carlos Arieles and his team published a paper exploring exactly this question. They used computer simulations to model what Sagittarius A star would look like if it were not a black hole, but instead a dense core of dark matter. Not just any dark matter, a specific kind. Fermionic dark matter. Matter made of particles that obey quantum rules, preventing them from being crushed into a single point. Particles that resist collapse, that build up internal pressure, that can form stable, ultra-dense cores without ever forming a singularity or an event horizon. And they found something remarkable. A dark matter core of sufficient density would bend light just as strongly as a black hole. The photons from the surrounding hot gas would still curve, they would still trace a ring, they would still create a central region of darkness. The image produced would be nearly identical to the black hole scenario, so close that with current instruments you could not tell the difference. This is not speculation, this is mathematical modelling. Published peer-reviewed, based on the same physics we use to model black holes, applied to a different type of object. Valentina Crespi, whose research we encountered earlier, put it plainly. Our model not only explains the orbits of stars and the galaxy's rotation, she said, but it is also consistent with the famous black hole shadow image. The dense dark matter core can mimic the shadow because it bends light so strongly, creating a central darkness surrounded by a bright ring. Let that sink in for a moment. The image that made headlines around the world. The image held up as proof of a supermassive black hole. That image is also consistent with a completely different kind of object. An object with no event horizon, no singularity, no point of infinite density, just an extraordinarily compact ball of invisible matter held together by quantum pressure, bending space-time through sheer gravitational weight. Does this mean the Event Horizon Telescope image is wrong? No, absolutely not. The image is real. The data is solid. The scientists who produced it did extraordinary work under extraordinarily difficult conditions. What it means is that the image alone cannot tell us what type of object we are looking at. It shows us the effects of extreme gravity. But it does not, by itself, distinguish between a black hole and a sufficiently dense alternative. This is a subtle but crucial distinction. In science, proving something exists and identifying exactly what it is are two different challenges. The Event Horizon Telescope proved that something extraordinarily compact and massive sits at the galactic centre. It confirmed the location. It measured the size of the shadow region. It gave us visual evidence consistent with decades of orbital data. But it did not close the case. It did not eliminate alternative models. It left the door open, just slightly, for other possibilities, and this is where the story deepens. Because if a dark matter core can mimic a black hole so precisely matching the stellar orbits, matching the shadow, matching every observation we have made so far, then how do we tell them apart? The answer lies not in what we have already seen, but in what we have not yet been able to observe. There are predictions, subtle differences, tiny discrepancies that only appear under the most extreme conditions, in the finest details, at the very edge of what our instruments can detect. A true black hole has an event horizon, a boundary of no return. And near that boundary, light does something extraordinary. Photons can orbit the black hole multiple times, spiraling closer and closer before either escaping or falling in. This creates something called a photon ring, a faint nested set of rings inside the main shadow, a signature unique to black holes. A dark matter core, no matter how dense, would not produce photon rings. Not in the same way. Because without an event horizon, without that sharp boundary, light behaves differently. It bends, it curves, but it does not get trapped in those endless spiraling orbits. Detecting photon rings would settle the question. But they are incredibly faint, far below the resolution of the current Event Horizon Telescope. Seeing them will require the next generation of instruments. Larger arrays, space-based telescopes, interferometers that combine signals from observatories separated by the distance between Earth and orbit. NASA has proposed such a mission, the Black Hole Explorer, a space-based radio telescope designed to link directly with the next generation Event Horizon Telescope, creating a virtual dish larger than the planet itself. If built, it could image photon rings. It could peer deeper into the shadow. It could, perhaps, give us the proof we need. But that mission is years away, maybe decades. Until then, we are left with an image. A beautiful, haunting, carefully crafted image of a glowing ring and a dark centre. An image consistent with everything we know, and an image that for now holds its secrets close. The shadow does not lie, but it does not tell the whole truth either. Not yet. We know how stars are born. We understand it in deep, beautiful detail. Gas and dust collapse under gravity. The core heats up. Nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing energy, and a star begins to shine. We have seen this process at every stage. We have watched it happen in real time across the galaxy. We also know how stars die. Smaller stars, like our Sun, swell into red giants, shed their outer layers, and leave behind dense cores called white dwarfs. Larger stars go out more violently. When they exhaust their nuclear fuel, their cores collapse in a fraction of a second. The outer layers rebound in a supernova explosion so bright it can briefly outshine an entire galaxy, and what remains at the centre if the star was massive enough, is a black hole. A stellar black hole. A few times the mass of the Sun, compressed into a sphere only a few kilometres across. These objects are well understood. We have detected dozens of them. We know how they form. We know where to find them. We can predict their properties with confidence. Some astronomers estimate there may be as many as 1 billion stellar black holes scattered throughout the Milky Way. 1 billion silent, invisible remnants of stars that lived, burned, and collapsed. They drift through the galaxy, occasionally revealing themselves when they pull matter from a companion star or when they merge with another black hole, sending gravitational waves rippling across space-time. This is settled science. The kind of knowledge you will find in textbooks, taught in universities, confirmed by decades of observation and theory working hand in hand. But now we must confront something uncomfortable. A gap in that knowledge so large, so fundamental, that it quietly shakes the foundation of everything we think we understand about the universe. We do not know how supermassive black holes form. Not at all. Not even a little. We have theories, yes, educated guesses, models and simulations, but no definitive answer. No clear path from the well-understood physics of stellar collapse to the monsters that sit at the centres of galaxies. And Sagittarius A star is one of those monsters. 4.3 million times the mass of the Sun. Millions, not tens, not hundreds. Millions that is not just a bigger version of a stellar black hole. It is a completely different category of object. And the problem is this: there is no known star massive enough to collapse and create something like Sagittarius A star. The most massive stars we have ever observed top out at around 200 to 300 times the mass of the Sun. And even those giants do not leave behind black holes anywhere near the size of Sagittarius A star. When they collapse, much of their mass is blown away in the supernova explosion. What remains is a stellar black hole. Massive, yes, but measured in tens or perhaps 100 solar masses, not millions. So if supermassive black holes cannot form from the collapse of a single star, how do they form? One possibility is that they grow over time. A stellar black hole forms first, through the normal collapse of a massive star. Then it begins to feed. It pulls in gas and dust from its surroundings. It swallows other stars. It merges with other black holes. Slowly, over millions or billions of years, it grows larger and larger, accumulating mass the way a snowball rolling downhill gathers snow. This process is called accretion. And it definitely happens. We have observed black holes feeding. We see the bright disks of superheated matter spiralling inward. We detect X-rays and gamma rays from the violent friction and collisions. Growth by accretion is real. But here is the problem. It is slow. Incredibly slow. Even under ideal conditions, a black hole can only grow so fast. There are physical limits. As matter falls inward, it heats up and radiates energy. That energy pushes outward, creating pressure that resists further infall. This is called the Eddington limit, named after the astrophysicist Arthur Eddington, who first described it. Because of this limit, a stellar black hole feeding continuously at the maximum possible rate would still take billions of years to reach millions of solar masses. And that would be fine, except for one glaring issue. We see supermassive black holes in the early universe, very early, less than 1 billion years after the Big Bang. Thanks to the James Webb Space Telescope, we can now peer back to a time when the universe was still in its infancy, and we find galaxies already harbouring supermassive black holes. Hundreds of millions of solar masses. sometimes billions. Sitting at the centres of galaxies that themselves should barely have had time to form, there simply has not been enough time for those black holes to grow from stellar seeds through accretion alone. The math does not work. The timescale is too short. So scientists proposed alternatives. Maybe the seeds were larger to begin with. Maybe instead of starting from a stellar black hole of 10 or 20 solar masses, the process began with something bigger. An intermediate mass black hole, thousands or tens of thousands of solar masses, formed not from a single star, but from a dense cluster of stars colliding and merging in the chaotic early universe. This could work in theory. It would give the black hole a head start. More mass to begin with means less time needed to grow to supermassive scales. But we have very little evidence for intermediate mass black holes. A few candidates have been detected, but they are rare and difficult to study. We do not know how common they were in the early universe. We do not know if they formed often enough to explain every supermassive black hole we see. Another idea is even more radical. Perhaps supermassive black holes do not grow at all. Perhaps they form directly. Massive clouds of gas in the early universe, too hot or turbulent to form stars, collapsing straight into black holes. Skipping the stellar phase entirely. This is called direct collapse. And it is mathematically possible under very specific conditions. The gas must be extremely pure, mostly hydrogen and helium, with almost no heavier elements. It must be hot enough to resist fragmenting into smaller clumps. And it must collapse fast, all at once, before stars have a chance to form and disrupt the process. In simulations, this can produce black holes of 10,000 to 100,000 solar masses in a single event, much closer to supermassive scales. But again, we have no direct evidence this actually happens. We have never observed a direct collapse in progress. We do not know how often it occurred. We cannot confirm it is the answer. And so the question remains open. Unresolved, hanging in the balance. This is not a minor gap in our knowledge. This is foundational. Supermassive black holes are not rare curiosities. They appear to exist at the centre of nearly every large galaxy in the universe, including ours. If we do not understand how they form, we do not fully understand galaxies. We do not fully understand how the universe evolved from the smooth, almost featureless state shortly after the Big Bang to the rich, structured cosmos we see today. The formation of supermassive black holes is one of the great unsolved problems in astrophysics. It sits alongside dark matter and dark energy as a fundamental mystery, a place where our best models run out of answers. And this is where the dark matter core hypothesis enters the picture in a quietly powerful way. Because if Sagittarius A star is not a black hole that had to form and grow through some unknown process, but instead a dense core of fermionic dark matter that could have existed from the very beginning or assembled far earlier than any star-based black hole, could then the formation problem disappears. Dark matter was present in the early universe. It was there before the first stars ignited. It shaped the structure of the cosmos, pulling gas into the regions where galaxies would eventually form. If dark matter can clump together into dense cores, it does not need to wait for stars to collapse, or for slow accretion to build mass over billions of years. It could form early. Quickly, naturally, simply by the forces already at work in the young universe. This does not prove the dark matter model is correct. But it does something important. It offers a solution to a problem that the black hole model cannot yet solve. And in science, when one theory answers a question the dominant theory struggles with, that theory deserves a closer look. A much closer look. Sometimes the most important questions in science come from the most unexpected places. Not from grand theories or billion-dollar telescopes, but from a quiet voice asking, "What if we are wrong?" In February of 2026, that quiet voice belonged to Valentina Crespi. Doctor. Crespi works at the Institute of Astrophysics in La Plata, Argentina. She studies dark matter at galactic scales, the invisible substance that holds galaxies together, that shapes the largest structures in the universe, that makes up more than 80% of all the matter that exists. Her work typically focuses on the outer regions of galaxies, where dark matter's influence is most obvious, the places where stars move too fast for the visible matter alone to explain their motion. But Crespi had been thinking about the centre, about Sagittarius A star, about the decades of observations that pointed so convincingly toward a supermassive black hole. And she had been wondering, what if there was another explanation? Not because the black hole model was wrong. It worked beautifully. It fit the data with remarkable precision. But because other possibilities had never been tested with the same rigour. Other ideas had been proposed over the years, exotic objects, alternative theories, but they had remained largely theoretical. Mathematical curiosities. No one had taken the time to compare them directly to the real measured motions of the stars orbiting Sagittarius A star. Crespi decided to change that. Working with an international team of collaborators, she focused on one specific alternative, a dense core of dark matter, not the diffuse, spread-out dark matter that surrounds galaxies like vast invisible halos, but dark matter compressed. Concentrated, squeezed into a region so small and dense that it could mimic the gravitational effects of a supermassive black hole. The idea was not new. Scientists had proposed dark matter cores before. But previous work had been mostly theoretical, models and equations without detailed comparisons to observational data. Crespi's approach was different. She wanted to test the idea rigorously, scientifically, to pit it directly against the black hole model and see which one matched reality more accurately. She gathered the best available data on the objects closest to Sagittarius A star, the S stars, those impossibly fast-moving points of light that orbit the galactic centre, and the G objects, those strange, shape-shifting clouds that stretch and deform as they approach the central mass. These objects are crucial because they spend their lives in the most extreme gravitational environment in our galaxy. Their motions are determined entirely by the mass and structure of whatever sits at the centre. If you can model their orbits accurately, you can understand the nature of the central object. If your model fails to match their paths, it fails entirely. Crespi focused on 6 objects in particular. The star S2, whose 16-year orbit had been tracked with exquisite precision for decades, and 5 of the known G objects, each following its own elliptical path around the galactic centre. S2 was especially important because its orbit is so well measured. Every time it completes a loop around Sagittarius A star, astronomers can track its position with incredible accuracy. They can measure how its speed changes as it swings closer to the centre and then farther away. They can watch how its path shifts slightly with each orbit due to the effects of general relativity, the same effects that cause Mercury's orbit around the Sun to precess, but magnified by the extreme gravity near Sagittarius A star. The G objects added another layer of complexity. These are not simple point sources like stars. They are extended objects clouds or cocoons of material that respond to gravity not just through their orbital motion, but through their shape. As they approach Sagittarius A star, they stretch and elongate, pulled by the difference in gravitational force between their near and far sides. This process is called tidal stretching, and it reveals subtle details about the gravitational field that simple stellar orbits cannot. Any successful model of Sagittarius A star must reproduce both effects: the precise orbital mechanics of S2 and the complex tidal deformation of the G objects. For her dark matter model, Crespi used a specific type of theoretical particle called a fermion. Fermions are the building blocks of ordinary matter: electrons, protons, neutrons. They obey a quantum mechanical rule called the Pauli exclusion principle, which prevents two identical particles from occupying the same space at the same time. This rule is why matter has structure, why atoms do not collapse, why you cannot walk through walls. Dark fermions would obey the same rule. They could clump together under gravity, forming dense cores, but they could not collapse infinitely. The exclusion principle would create internal pressure, pushing back against further compression. This pressure would stabilize the core, preventing it from forming a singularity or an event horizon. The result would be an object that could reach enormous density comparable to a black hole, but would remain a sphere of material rather than a point of infinite compression. Crespi fed this model into computer simulations. She calculated how S2 and the G objects would move in the gravitational field of a dense fermionic dark matter core. She adjusted the parameters, the mass, the size, the internal structure, to find the best fit to the observational data. And then she compared her results to the black hole model. What she found was extraordinary. The dark matter core reproduced the observations with less than 1% difference from the black hole model. Less than 1%. The orbits of S2 matched. The behavior of the G objects matched. The precession effects matched. The tidal stretching matched. Every measurement, every detail, every subtle effect was accounted for with nearly identical accuracy. This was not approximate agreement. This was not close enough. This was precision modelling. Statistical analysis. The kind of rigorous comparison that forms the foundation of modern astrophysics. Crespi published her results in the monthly notices of the Royal Astronomical Society, one of the most respected journals in astronomy. The paper was peer-reviewed by independent experts. It passed every check. And when it appeared in print, it did something that few scientific papers accomplish. It reopened a question that many had considered settled. What this means is profound, but subtle. Crespi had not proven that Sagittarius A star is a dark matter core. She had not disproven the black hole model. What she had shown was that the two models are observationally indistinguishable given current data. You cannot tell them apart by looking at stellar orbits. You cannot tell them apart by studying G-object behavior. Both models explain the data equally well. Both pass the same tests. Both make the same predictions for the motions of objects near the galactic center. This is both exciting and frustrating. Exciting because it means we have a viable alternative to explore. Frustrating because it means the data we have spent decades collecting cannot, by itself, tell us which model is correct. But there is something else. Something that makes Crespi's work more than just an academic exercise in alternative theories. If Sagittarius A star truly is a dense core of dark matter, it would not be an isolated object. It would be connected to the rest of the galaxy in a way that no black hole could be. Dark matter cores could extend outward, forming the very halo structure that surrounds the Milky Way. They could be part of a single continuous distribution of invisible matter stretching from the galactic center to the outer edges and beyond. In other words, Crespi's model does not just explain Sagittarius A star, it potentially connects two of the biggest mysteries in modern physics. The nature of the galactic center. and the nature of dark matter itself, it suggests that the answer to both questions might be the same, that the darkness at the heart of our galaxy and the darkness that fills the cosmic web are not separate phenomena, but different expressions of the same underlying reality. That is a big idea, a beautiful idea, an idea that if true would change our understanding of how galaxies form, how the universe evolved, and what most of it is actually made of. But ideas, no matter how beautiful, must be tested. And that testing has only just begun. Imagine the universe as a vast library, endless shelves stretching in every direction, filled with books. But here is the strange thing. For every book you can see, for every volume you can pull from the shelf and read, there are 5 more books that are completely invisible. You cannot see them. You cannot touch them. You cannot open them or know what they contain. But you know they are there. You know because the shelves sag under their weight. You know because when you try to rearrange the visible books, they move as if surrounded by other volumes pushing back. You know because the entire library behaves as if it contains far more material than you can actually observe. This is the reality of our universe. For every gram of ordinary matter, every star, every planet, every atom in your body there are roughly 5 grams of something else, something invisible, something that interacts with gravity but remains stubbornly, mysteriously hidden from every instrument we have built to detect it. We call it dark matter. The name is almost poetic in its simplicity. Dark because it does not emit light. Dark because it does not reflect light. Dark because it does not absorb light. And matter because it clearly has mass. It pulls. It tugs on galaxies, on star clusters, on the largest structures in the cosmos. It shapes the universe through gravity alone, like a sculptor working with invisible clay. But what is it? What is this substance that makes up more than 80% of all the matter that exists? What are these phantom books filling the cosmic library? We do not know. That is not a confession of ignorance or a temporary gap in our knowledge that will be filled next year or next decade. It is one of the deepest, most persistent mysteries in all of science. We have been searching for dark matter for nearly a century. We have built underground laboratories. We have sent detectors into space. We have smashed particles together at energies that recreate the conditions a fraction of a second after the Big Bang. And still, it hides. The first hint of its existence came in 1933 from a Swiss astronomer named Fritz Zwicky. Zwicky was studying the Coma Cluster, a group of thousands of galaxies bound together by gravity, located about 300 million light-years from Earth. He was measuring how fast these galaxies were moving relative to each other, expecting to find a calm, orderly system held in balance by the gravitational pull of all the visible matter. Instead, he found chaos. The galaxies were racing around at speeds of more than 2,000 kilometers per second, speeds so high that, according to the laws of physics, they should have flung themselves apart long ago. The cluster should have dissolved, scattered across the cosmos like marbles thrown from a spinning bowl. But it had not dissolved. The Coma Cluster was stable. It had existed for billions of years. Something was holding it together. Something with enormous gravitational pull. Something invisible. Zwicky calculated how much matter would be needed to keep those galaxies bound in their cosmic dance. And he found that there was not enough visible matter, not even close. He would need at least 10 times more mass than he could actually see. 10 times more stars, more gas, more everything. Since the missing matter was invisible, he gave it a name. Dunkel Materie. dark matter. For decades, Zwicky's discovery was largely ignored. Dark matter seemed too strange, too unlikely. Perhaps he had made a mistake in his measurements. Perhaps there was more ordinary matter than he realized: dim stars, cold gas clouds, objects too faint to detect with the telescopes of the time. But the evidence kept accumulating. In the 1970s, astronomer Vera Rubin was studying individual galaxies. Not clusters, but single spiral galaxies like our own Milky Way. She was measuring how fast stars move in their orbits around the galactic centre, and she expected to find a simple pattern. Stars closer to the centre should move faster, pulled by the strong gravity of all the mass concentrated there. Stars farther out should move slower, like planets in our solar system where distant worlds like Neptune crawl along their orbits, while inner planets like Mercury race around the Sun. But that is not what Rubin found. Instead, she discovered that stars in the outer regions of galaxies were moving just as fast as stars closer to the centre. Sometimes faster. They were moving so quickly that they should have been flung out into intergalactic space, escaping the galaxy entirely. But they remained in their orbits year after year, century after century. Something was holding them in place. Something with mass. Something invisible. Galaxy after galaxy showed the same pattern. The rotation curves graphs showing orbital speed versus distance from the centre were flat. Constant, nothing like what you would expect from the distribution of visible matter alone. And so dark matter shifted from a curious anomaly in distant galaxy clusters to a fundamental feature of every large galaxy in the universe, including our own. The Milky Way, we now believe, is embedded in a vast halo of dark matter, a roughly spherical cloud of invisible material stretching far beyond the visible disk of stars and gas. This halo contains perhaps 10 times more mass than all the ordinary matter in the galaxy combined. It extends hundreds of thousands of light years in every direction, a hidden architecture that shapes everything we can see. Our Sun orbits not just the visible centre of the galaxy, but the combined gravitational pull of ordinary matter and dark matter together. The spiral arms, the distribution of stars, the motion of gas clouds, all of it is influenced by this invisible scaffold, this cosmic framework we cannot touch or measure directly. We know dark matter exists because we can see its effects. When light from distant galaxies passes through regions rich in dark matter, the light bends. This is called gravitational lensing, and it allows us to map the distribution of dark matter across the universe. We can trace its influence on the formation of the largest cosmic structures. We can simulate how galaxies and galaxy clusters would form without dark matter, and the results look nothing like the universe we observe. Dark matter is not speculation. It is not a theoretical convenience. It is an observational necessity. But knowing it exists is not the same as understanding what it is. The candidates fill scientific papers and fuel decades of research. WIMPs, weakly interacting massive particles. Hypothetical remnants from the early universe that interact only through gravity and the weak nuclear force. Axion's ultralight particles proposed to solve other problems in particle physics, but which might also make up dark matter. Sterile neutrinos. Primordial black holes, exotic states of matter that exist nowhere on Earth but might be common in the cosmos. Each possibility leads to different predictions, different experiments, different ways of searching. Underground detectors wait for dark matter particles to collide with ordinary atoms. Space-based telescopes look for the telltale signatures of dark matter annihilation, the brief flashes that might occur when two dark matter particles meet and destroy each other. particle accelerators try to create dark matter in the laboratory, producing conditions energetic enough to bring it into existence, if only for a fraction of a second. And yet, it remains elusive. In late 2025, there was excitement when researchers claimed to find a possible signal in data from the Fermi telescope, a hint of dark matter annihilation in the galactic center. But follow-up studies were inconclusive. The signal might be real. It might be something else entirely. The question remains open. This is the context in which Valentina Crespi's work takes on deeper meaning. If Sagittarius A star is indeed a core of dark matter dense, stable, gravitationally dominant, it would not just explain the galactic center. It would give us something we have never had before. A dark matter laboratory. Right here in our own galaxy. Close enough to study in detail. Massive enough to test our theories against high-precision observations, and the specific type of dark matter her model requires fermionic dark matter offers something even more intriguing. A candidate that could explain not just the nature of dark matter, but also how objects like Sagittarius A star could form so early in cosmic history. Because fermions, unlike some other dark matter candidates, cannot be compressed infinitely. They obey quantum rules. They resist collapse. They could form stable, massive cores without the long, slow growth processes that challenge our understanding of supermassive black hole formation. It is an elegant solution. A bridge between two mysteries. The invisible architect of the cosmos, revealed not at the edges of galaxies where its influence is most obvious, but at the very center where it has been hiding in plain sight all along. In 1969, while humans were taking their first steps on the moon, two physicists in Italy were taking a different kind of step into the unknown. Remo Ruffini and Silvano Bonazola were working on a problem that seemed almost impossibly abstract. What would happen, they wondered, if dark matter was not made of some exotic, unknown type of particle, but of something more familiar, something that followed the same quantum rules as ordinary matter, but interacted only through gravity? Their idea was elegant in its simplicity, and it had been sitting quietly in scientific literature for more than 50 years, waiting for the right moment, the right observations, the right questions to bring it back into the light. They proposed that dark matter might be made of fermions. Fermions are not exotic or strange. They are the building blocks of everything you touch, everything you see, everything you are made of. Electrons are fermions. Protons are fermions. Neutrons are fermions. The atoms in your body, the air you breathe, the ground beneath your feet, all of it is constructed from particles that obey fermionic rules. The most important of those rules is something called the Pauli exclusion principle, named after Wolfgang Pauli, the Austrian physicist who discovered it in 1925. The principle sounds technical, but its effects are everywhere around you. It says that no two identical fermions can occupy the same quantum state at the same time. They cannot be in the exact same place with the exact same energy and the exact same spin. They must maintain some difference, some separation, some individuality, even at the smallest scales. This is why matter has structure, why atoms do not collapse into points, why the chair you are sitting in does not crumble into nothing, why your hand cannot pass through the wall. The electrons in those materials are fermions, and they push back against each other. They refuse to be squeezed into the same space. They create pressure. Resistance, stability. Now imagine dark matter made of similar particles, dark fermions. Invisible cousins of the electrons and quarks that make up ordinary matter, but particles that interact only through gravity. No electromagnetic force. No nuclear forces, just the gentle, persistent pull of mass-warping spacetime. These particles could clump together under gravity, just like ordinary matter. They could accumulate over cosmic time, drawn into the deep gravitational wells where galaxies would eventually form. But unlike ordinary matter, they would not radiate energy away. They would not cool and condense into stars. They would remain invisible, influencing the universe only through their gravitational effects. And here is where the Pauli exclusion principle becomes crucial. As dark fermions gathered together, pulled inward by their own gravity, they would resist infinite compression, just like electrons in a white dwarf star or neutrons in a neutron star. The exclusion principle would create internal pressure. The particles would push back against further collapse, fighting the inward pull of gravity with quantum mechanical force. Under the right conditions, this could create a stable configuration. A dense core of dark matter held in balanced gravity pulling inward, quantum pressure pushing outward. The core could become incredibly massive, incredibly compact, but it would not collapse into a singularity. It would not form an event horizon. It would remain a physical object, a sphere of material with a definite size and structure. And that sphere could mimic a black hole almost perfectly. The gravitational field outside a fermionic dark matter core would be indistinguishable from the field around a black hole of the same mass. Stars would orbit it in the same way. Light would bend around it by the same amount. Matter falling toward it would heat up and glow with the same intensity, creating the same bright ring we see in Event Horizon Telescope images. But inside, the physics would be completely different. No singularity. No point of infinite density where the laws of physics break down. No event horizon, no boundary of no return. Just a sphere of dark matter so dense that space and time curve dramatically around it, but not so dense that they tear. This is what Carlos Argeles and his team at the Institute of Astrophysics in La Plata have been exploring. Argeles, who leads the dark matter research group, has spent years refining models of fermionic dark matter cores. His calculations show that such an object could reach masses comparable to supermassive black holes while remaining stable over cosmic timescales. The numbers are striking. A fermionic dark matter core with the mass of Sagittarius A star, 4.3 million suns, would be compressed to a density where a teaspoon of the material would weigh as much as a mountain. But it would still be matter, still be particles with definite positions and properties held together by quantum pressure rather than collapsed beyond all recognition. And from the outside, you could not tell the difference. The elegance of this solution extends far beyond the galactic centre. Because fermionic dark matter would not just explain Sagittarius A star in isolation, it would connect the galactic centre to the broader structure of dark matter throughout the galaxy. In this model, the dense core at the centre and the diffuse halo surrounding the galaxy are not separate objects. They are two parts of the same continuous structure, different regions of the same fermionic dark matter distribution, ranging from extremely dense at the centre to sparse and spread out at the edges. This is something no other model of Sagittarius A star can claim. Every other hypothesis, black holes, boson stars, other exotic objects, treats the galactic centre as distinct from the galaxy's dark matter content. Only the fermionic model unifies them into a single, coherent picture. Think about what this means. For nearly a century, we have known that dark matter exists. We have mapped its influence on galaxy rotation curves, on gravitational lensing, on the large-scale structure of the universe. And for decades we have puzzled over the nature of supermassive black holes, wondering how they form so early, how they grow so quickly. The fermionic dark matter model suggests these are not separate mysteries. They are two aspects of the same phenomenon. The invisible scaffold that shapes galaxies and the massive objects that anchor their centres are made of the same material, governed by the same physics, part of the same cosmic architecture. It is a beautiful idea, the kind of unifying insight that occasionally emerges in science, connecting seemingly unrelated observations into a single elegant framework. But beauty alone is not enough. The model must make testable predictions. It must explain observations that the black hole model cannot. And there are hints that it might. The European Space Agency's Gaia mission has been mapping the motion of stars throughout the Milky Way with unprecedented precision. In 2022, Gaia data revealed something unexpected at the outer edges of the galaxy. A sharp drop-off in rotation speeds called Keplerian decline. Most dark matter models struggle to explain this observation. Their predictions are too smooth, too gradual. But fermionic dark matter, with its well-defined quantum properties and resistance to compression, could naturally create a dark matter halo with sharper boundaries. The exclusion principle would give the halo structure, edges, transitions that could match what Gaia observed. It is not proof. Not yet, but it is the kind of prediction that makes a theory worth pursuing. The kind of detail that separates viable ideas from mere speculation. And it points towards something profound, the possibility that the universe's most mysterious substance has been hiding not just in the empty spaces between galaxies, not just in the diffuse halos around them, but in the most prominent, most studied, most carefully observed objects in astronomy. Right at the centres of galaxies. Right where we have been looking all along. Disguised as black holes, waiting patiently for us to ask the right questions. What if the darkness at the heart of everything is not absence, but presence? Not emptiness, but fullness. Not the end of matter, but its most fundamental expression. The fermionic solution whispers that it might be. That the universe's greatest mystery and its most celebrated discovery might be the same thing, seen from different angles, through different lenses, with different assumptions about what we thought we knew. What if everything we thought we knew about the architecture of our galaxy was incomplete? Not wrong, exactly. The observations are real. The measurements are accurate. The patterns we see in star movements, in the distribution of gas and dust, in the way light bends around massive objects, all of that is genuine. But what if we have been looking at the pieces, without seeing how they fit together? For decades, astronomers have treated the Milky Way as a collection of separate components. At the centre, a supermassive black hole. Surrounding that, a bulge of older stars. Beyond that, the spiral disk where we live. And enveloping everything, like an invisible atmosphere, a halo of dark matter stretching far into space. Each component seemed distinct, formed at different times through different processes governed by different physics. The black hole grew through accretion and mergers. The stars formed from collapsing gas clouds. The dark matter halo assembled from primordial fluctuations in the early universe. Separate stories. Separate objects. Separate explanations. But what if they are not separate at all? What if the most massive, most dominant feature at the galactic centre and the vast invisible structure that surrounds the entire galaxy are not two different things, but two expressions of the same underlying reality? This is the radical proposition at the heart of the fermionic dark matter model. Not just that Sagittarius A star might be a dark matter core instead of a black hole, but that this core is connected physically, continuously, seamlessly to the dark matter that fills the space around us. In every other model of Sagittarius A star, the central object stands alone. A black hole is a discrete thing, a point in space-time with sharp boundaries. It might grow by pulling in surrounding material, but it remains fundamentally separate from its environment. The dark matter halo and the central black hole coexist in the same galaxy, but they are distinct structures with distinct origins. The fermionic model breaks down that separation completely. Picture a single, continuous distribution of dark fermions stretching from the very centre of the galaxy to its outermost edges and beyond. Near the centre, where gravity is strongest, the dark matter is compressed to extraordinary density, so dense it mimics a supermassive black hole. Moving outward, the density gradually decreases, but the material remains connected. No sharp boundaries, no sudden transitions, just a smooth gradient from the ultra-dense core to the sparse halo. It is like imagining the atmosphere of a planet. At sea level, air is thick and dense. As you climb higher, it becomes thinner and thinner, but there is no exact point where the atmosphere ends, no sharp line between air and space, just a continuous transition from dense to sparse, all part of the same connected structure. Now scale that idea up by factors of millions. Replace air with dark matter. Replace Earth with an entire galaxy, and you begin to glimpse what the fermionic model proposes. One structure. One continuous, connected, coherent distribution of invisible matter. Dense at the centre, sparse at the edges, but fundamentally unified. Governed by the same physics throughout. Made of the same particles. Shaped by the same balance between gravity and quantum pressure. This is not just elegant theory. It makes specific, testable predictions about how galaxies should behave, and some of those predictions are starting to match observations in ways that surprise even the scientists working on the model. Consider the problem of galaxy rotation curves. The graphs that show how fast stars move at different distances from the galactic centre. These curves were among the first evidence for dark matter, because they showed that stars in the outer regions of galaxies move faster than they should if only ordinary matter were present. Most dark matter models explain this by proposing a halo that extends far beyond the visible disk of stars. The halo provides additional gravity to keep the fast-moving outer stars in their orbits, and for the most part, this explanation works well. It matches the basic shape of the rotation curves. It explains why galaxies hold together. But the details have always been tricky. Different types of dark matter, hot, cold, warm, interacting, non-interacting, make slightly different predictions. Some models predict rotation curves that rise too steeply. Others predict curves that remain flat too far out. Getting the exact shape right across all types of galaxies has been a persistent challenge. Fermionic dark matter offers a different approach. Because fermions obey the exclusion principle, because they resist compression beyond a certain point, they naturally create dark matter distributions with more structure. More definition, sharper transitions between dense and sparse regions. And in 2022, the European Space Agency's Gaia mission provided data that seemed almost designed to test this prediction. Gaia is mapping the motion of more than 1 billion stars throughout the Milky Way. Its goal is to create the most detailed, three-dimensional map of our galaxy ever attempted. And buried in Gaia's data was something unexpected. At the very outer edges of the galactic disk, the rotation curve does not stay flat indefinitely. Instead, it begins to drop. Stars farther out move slower than stars closer in, following what astronomers call a Keplerian decline, the same pattern you see in planetary systems, where outer planets move more slowly than inner ones. This observation was puzzling for most dark matter models. In traditional scenarios, the dark matter halo should extend smoothly outward, providing consistent gravitational support across large distances. There should be no sharp drop-off, no sudden transition to Keplerian motion. But fermionic dark matter could explain it naturally. If the dark matter halo has a more defined structure, if the exclusion principle creates a boundary where the halo density drops more sharply, then you would expect exactly what Gaia observed. A transition region where the galaxy's rotation curve changes character, where the influence of the central dark matter structure gives way to the simpler gravitational dynamics of isolated objects. It is a subtle effect, the kind of detail that only becomes visible with extremely precise measurements across vast numbers of stars, but it is exactly the kind of observational signature that could distinguish between different dark matter models. Valentina Crespi and her collaborators have noted this connection explicitly. Our model not only explains the orbits of stars and the galaxy's rotation, she has said, but it is also consistent with the rotation patterns Gaia revealed. The fermionic structure would naturally produce the sharp boundaries needed to match the observations. This is how science advances, not through sudden dramatic revelations, but through the accumulation of small details that favour one explanation over another. The orbital motions of S stars near the galactic centre, the stretching of G objects, the shadow in the Event Horizon Telescope image, the rotation curve at the galaxy's outer edge. Each observation by itself might be explained multiple ways, but together they begin to paint a picture, and the picture emerging from the fermionic dark matter model is remarkable. It suggests that two of the greatest mysteries in modern astrophysics, the nature of dark matter and the nature of supermassive black holes, might not be separate puzzles at all. They might be the same puzzle, viewed from different perspectives. Dark matter shapes the largest structures in the universe. It determines how galaxies form, how they cluster, how they evolve over cosmic time. If Sagittarius A star is indeed the dense core of our galaxy's dark matter distribution, then studying it could teach us about dark matter everywhere. Not just its gravitational effects, but its fundamental properties, its particle nature, its quantum behavior, its role in cosmic evolution. At the same time, understanding Sagittarius A star as a fermionic core could resolve some of the deepest problems in black hole physics. How supermassive black holes form so early in cosmic history, why they seem to exist at the centre of every large galaxy, how they achieve such enormous masses so quickly, if they are not black holes at all, but dark matter cores that could form naturally in the early universe, then these problems simply disappear. It is a beautiful synthesis. A way of connecting observations across vast scales of space and time into a single, coherent story. From the quantum mechanics of individual particles to the structure of entire galaxies. From the first moments after the Big Bang to the present day. But beauty, as always in science, is not enough. The model must continue to make predictions. It must suggest new observations, new tests, new ways of probing the nature of reality. And those tests are coming. There is something almost maddening about the fermionic dark matter model. It fits the data, it explains the observations, it connects two of the deepest mysteries in physics into a single, elegant solution. But it does so by being almost perfectly hidden, almost perfectly indistinguishable from what we already thought we knew. The orbital motions of S stars around Sagittarius A star, a fermionic dark matter core, predicts the same paths as a black hole. The stretching and deformation of G objects, both models explain it equally well. The shadow captured by the Event Horizon Telescope, dark matter bends light just as strongly as a black hole of the same mass. It is as if the universe has presented us with a riddle designed to test the limits of human ingenuity. two completely different explanations that produce nearly identical effects. Two theories that make the same predictions for almost every observation we can currently make. But almost is the key word. Because while the two models are remarkably similar, they are not perfectly identical. There are subtle differences, tiny discrepancies that appear only under the most extreme conditions, in the finest details, at the very edge of what our instruments can detect. The challenge is building instruments sensitive enough to see those differences. The most promising signature lies in something called photon rings. These are among the strangest predictions of black hole physics, and they exist only in the immediate vicinity of an event horizon. Near a black hole, gravity becomes so strong that light itself can orbit. Photons, particles of light, can circle the black hole multiple times before either escaping to infinity or falling past the event horizon forever. This creates a series of nested rings in the black hole's shadow. Faint, overlapping circles of light that spiral inward like the grooves on an old phonograph record. These photon rings are a direct consequence of the event horizon. They form because there is a sharp boundary, a point of no return, where the physics changes abruptly. Light that crosses this line is doomed. Light that stays just outside can orbit indefinitely. A fermionic dark matter core would create no such rings. Without an event horizon, without that sharp boundary between escape and capture, light would simply bend smoothly around the dense core. It would curve, it would focus, but it would not get trapped in the endless spiraling orbits that create the nested ring structure. Detecting photon rings would settle the question immediately. Their presence would confirm a black hole. Their absence would support the dark matter model. But photon rings are incredibly faint. Current telescopes cannot see them. The Event Horizon Telescope, for all its remarkable achievements, lacks the resolution and sensitivity required. The rings are there according to theory, but they hide just beyond our ability to detect them. NASA has proposed a solution. The Black Hole Explorer mission would place a radio telescope in space, far from the interference of Earth's atmosphere. This space-based observatory would link directly with ground-based telescopes to create an interferometer larger than the Earth itself. The combined system would have the resolution needed to image photon rings, if they exist. The mission is still in the planning stages. Funding must be secured. Technology must be developed. International partnerships must be arranged. If everything goes perfectly, the Black Hole Explorer might launch within the next decade. More realistically, it could take much longer. Until then, astronomers are pushing current instruments to their absolute limits. The gravity interferometer at the Very Large Telescope in Chile represents the cutting edge of ground-based astronomy. Gravity combines light from 4 separate 8-meter telescopes, creating an instrument with the resolution of a telescope 130 meters across. It can track the motion of stars near Sagittarius A star with incredible precision. Gravity has already measured something remarkable. As S2 completes its 16-year orbit around the galactic center, its path shifts slightly with each loop. This is called pericenter precession, and it happens because space and time are warped by the central mass. The stronger the gravity, the more dramatic the precession. Both the black hole and fermionic dark matter models predict precession. But they predict slightly different amounts. The difference is small, only a few %, but it might be measurable with enough precision and enough time. Every orbit of S2 provides more data. Every passage close to the galactic center adds another data point to the growing collection of measurements. Over decades, the accumulated precision might be enough to distinguish between the two models. But ground-based observations, no matter how sophisticated, have limits. The atmosphere blurs starlight. Weather interrupts observations. Even the best adaptive optics cannot completely compensate for the turbulence of air above the telescopes. Space-based missions offer another path forward, but they require patience and substantial investment. At the other end of the scale, the smallest scale direct detection experiments are hunting for dark matter particles here on Earth. The NEON experiment in South Korea is designed specifically to search for dark fermions. Deep underground, shielded from cosmic rays and background radiation, sensitive detectors wait for the rare collision between a dark matter particle and an ordinary electron. If dark fermions exist, they should be everywhere, streaming through the galaxy, passing through your body right now. Most of them would interact so weakly that they pass through matter as if it were not there. But occasionally, perhaps once every few months in a detector the size of a small room one, might collide with an electron, transferring a tiny amount of energy. NEON and similar experiments around the world are designed to catch these rare events. They measure energy deposits down to individual electron volts. They filter out background noise from radioactive decay, cosmic rays, and human activity. They search for the specific signature that dark fermions would produce. So far, no confirmed detection. But the technology improves every year. The detectors become more sensitive. The background noise is better understood. The search continues. A direct detection of dark fermions would not prove that Sagittarius A star is made of dark matter. But it would confirm that such particles exist, making the galactic center hypothesis much more plausible. Meanwhile, other observations could test different aspects of the fermionic model. The James Webb Space Telescope has revealed strange objects in the early universe called little red dots. These are compact, massive structures that appear to exist in galaxies less than 1 billion years after the Big Bang. They are difficult to explain if they are supermassive black holes, because there has not been enough time for such massive objects to form and grow through conventional processes. But if they are fermionic dark matter cores, they could have formed much earlier. They would not need to wait for the first stars to collapse, or for slow accretion to build mass over billions of years. They could have condensed directly from the dark matter that filled the early universe. Detailed spectroscopy of these little red dots might reveal whether they behave like black holes or like something else. Future observations with Webb and other telescopes could test whether the fermionic model explains their properties better than conventional theories. Each of these approaches, photon ring detection, improved orbital measurements, direct particle detection, early universe observations, offers a different window into the question. No single experiment is likely to provide a definitive answer. But together, over the coming years and decades, they could build a compelling case for one model or the other. Science often advances not through sudden breakthroughs, but through the gradual accumulation of evidence. Small improvements in precision. New instruments with better sensitivity. Creative approaches to old problems. The fermionic dark matter model has opened a door that many thought was closed. It has transformed a settled question into an active area of research. It has given astronomers new reasons to build better telescopes, to design more sensitive experiments, to look more carefully at data they thought they already understood. Whether the model proves correct or not, it has already accomplished something valuable. It has reminded us that even our most confident conclusions rest on evidence that can be reinterpreted, that the universe may still hold surprises in the places we thought we knew best. And sometimes the most important discoveries come not from finding something new, but from realizing that something familiar was never quite what we thought it was. Imagine for a moment that it is true, not proven yet, not settled beyond all doubt, but true nonetheless. Imagine that the decades of patient observation, the Nobel Prize winning measurements, the stunning images from the Event Horizon telescope have all been pointing towards something real, but not quite what we thought. Imagine that Sagittarius A star is not a black hole. Imagine that the 4.3 million solar masses sitting at the centre of our galaxy, the object that controls the motion of every star in the Milky Way, the gravitational anchor around which our entire cosmic home revolves, is something far stranger and far more familiar than we ever dared to consider. A sphere of dark matter, dense beyond comprehension, massive beyond imagination, but made of the same invisible substance that fills the space between stars, that holds galaxies together, that shapes the largest structures in the universe. Not absent matter, but present matter. Not emptiness, but fullness. Not the end of physics, but physics expressing itself in its most fundamental form. If this is true, if the fermionic dark matter model captures something essential about reality, then everything changes. Not just our understanding of one object in one galaxy, not just another entry in astronomy textbooks, or another theory for graduate students to debate. Everything, the way we think about matter and energy, about structure and emptiness, about the visible and invisible architecture of existence itself. Consider what it would mean for our understanding of dark matter. For nearly a century, we have known that most of the universe is made of something we cannot see. We have mapped its influence across cosmic scales. We have traced its gravitational fingerprints in the rotation of galaxies, the formation of galaxy clusters, the bending of light across billions of light years. But we have never touched it, never detected it directly, never known what it truly is. The fermionic dark matter model suggests it has been hiding in the most obvious place imaginable. Not scattered uniformly through empty space, not confined to the invisible halos around galaxies, but concentrated into dense cores that we have been studying intensively for decades. The very objects we thought were black holes, the phenomena that have captured public imagination, inspired countless research projects, earned Nobel Prizes, might actually be dark matter laboratories. Right here in our own galaxy, 27,000 light-years away, close enough to study in exquisite detail with the best instruments humanity can build. If Sagittarius A star is a fermionic core, then we have not been studying a collapsed star or a wound in space-time. We have been studying the universe's most abundant form of matter in its most concentrated state. Every observation of stellar orbits, every measurement of gravitational effects, every image of the central shadow becomes a probe into the nature of dark matter itself. The implications ripple outward like waves from a stone dropped in still water. Dark matter would no longer be purely hypothetical. It would have location, structure, measurable properties. We could determine its density profile, its response to gravitational stress, the way it interacts with ordinary matter falling toward it. We could test theories about dark matter particle physics against real data from a real object. And the connections would extend far beyond the galactic centre. If the dense core and the diffuse halo are part of the same continuous structure, then studying Sagittarius A star teaches us about dark matter everywhere. The quantum properties that create pressure in the central core are the same properties that shape the distribution of dark matter throughout the galaxy, throughout galaxy clusters, throughout the cosmic web itself. One laboratory. One object. Revealing the nature of 85% of all the matter in the universe. But the revelations would not stop with dark matter. Consider what the model means for our understanding of cosmic evolution. The early universe was simpler than the cosmos we see today. No stars, no planets, no galaxies, just hydrogen, helium, and dark matter in an expanding, cooling sea of particles and radiation. From that simple beginning, over 14 billion years, emerged the rich complexity of the modern universe. We understand much of that story, how the first stars ignited, how heavy elements were forged in stellar cores, how galaxies assembled from smaller building blocks. But we have struggled to explain one crucial piece: how supermassive black holes appeared so early, grew so quickly, became so massive before the universe had much time to evolve. The fermionic model dissolves that problem entirely. Dark matter cores could form directly from the primordial material of the early universe. No need to wait for the first stars to collapse. No need for slow accretion over billions of years. Just the natural tendency of dark fermions to clump together under gravity while resisting infinite compression through quantum pressure. The little red dots discovered by the James Webb Space Telescope, those mysterious massive objects in infant galaxies, would no longer be puzzling. They would be natural, expected, inevitable consequences of the same physics that creates fermionic cores today. The timeline of cosmic evolution would shift. The role of dark matter would expand from passive scaffold to active architect. The formation of galaxies, the seeding of structure, the emergence of the complex universe, we inhabit all of it influenced by the quantum properties of invisible particles that were present from the very beginning. And then there is the deeper question, the philosophical question that touches something beyond astronomy, beyond physics, beyond science itself. What does it mean that we live in a universe where the most massive, most dominant objects in every galaxy might be made of the same substance that flows through the empty space around us? Where the centers of cosmic power are built not from the bright, energetic matter we see and touch, but from the quiet, invisible matter we have spent decades trying to understand. It suggests a universe far more unified than we imagined. Not a collection of separate phenomena governed by separate laws, but a single, interconnected system where the same fundamental physics creates structure on every scale. From the quantum properties of individual particles to the formation of galactic cores. From the first moments after the Big Bang to the slow dance of stars around invisible centers. It hints at an elegant simplicity beneath apparent complexity. The same exclusion principle that prevents electrons from occupying identical quantum states the rule that gives atoms their structure and matter its stability might also shape the cores of galaxies and determine the fate of cosmic evolution. We would be living not in a universe divided between the seen and unseen, the ordinary and exotic, the familiar and strange, but in a universe where those apparent divisions dissolve under closer inspection, where the invisible architecture that surrounds us is made of the same essential ingredients as the visible structures we celebrate, where darkness and light are not opposites, but partners in the same cosmic dance. The fermionic dark matter model whispers that the universe might be more beautiful, more interconnected, more comprehensible than we thought. That two of the greatest mysteries in modern science are really one mystery seen from different angles. That the answer to questions we have been asking separately for decades might be the same answer, waiting patiently for us to realize what we were looking at. This would not diminish the wonder of black holes or dark matter or the cosmos itself. If anything, it would amplify it. It would reveal a universe where the most exotic phenomena emerge from the same quantum rules that govern ordinary matter, where the strangest objects in the cosmos are built from ingredients that surround us constantly, where the darkness at the heart of every galaxy connects seamlessly to the darkness that fills the space between stars. It would be a universe where we are not separate from the cosmic mystery, but embedded within it, made of the same particles that shape galactic centers, surrounded by the same invisible matter that determines cosmic structure, connected through the fundamental forces of physics to the largest and most powerful objects in existence. In such a universe, looking up at the night sky becomes a different kind of experience. Not gazing outward at distant alien phenomena, but looking inward at the extended body of a single, unified cosmic organism of which we are an integral part. The darkness between the stars would no longer seem empty. The invisible halo around our galaxy would no longer seem abstract. The monster at the galactic centre would no longer seem separate from the gentle forces that shape our everyday existence. All of it. Connected, unified, one. Wind down, and so we come to the end of this journey through darkness and light, through the seen and unseen, through the questions that define our place in the cosmos, whether Sagittarius A star is a black hole or a core of dark matter, whether the universe reveals its secrets through photon rings or direct detection experiments, the deeper truth remains unchanged. We are part of something larger than ourselves, something more interconnected, more elegant, more mysterious than our everyday experience suggests. The same physics that allows you to breathe, that gives structure to the atoms in your body, that creates the stable matter beneath your feet, extends across 27,000 light-years to shape the gravitational heart of our galaxy. You are made of stardust, yes, but you are also surrounded by, embedded within, connected to the invisible architecture that holds everything together. Every breath you take moves through space filled with dark matter. Every heartbeat resonates with the same quantum rhythms that might create cosmic cores millions of times more massive than the sun. The mystery is not separate from you. You are part of it. Woven into it, a conscious expression of the same universe that creates galaxies and bends light and spins stars in their ancient orbits around invisible centres. Rest now in that connection. Let the questions settle into the quiet spaces between thoughts. Trust that the cosmos continues its patient work of revelation, whether you are awake to witness it or asleep to dream of it. The universe that holds you also holds the answers. In time, in its own time, it will share them. The darkness is not empty. It is full of matter, full of mystery, full of possibilities yet to be discovered. Full of you. Close your eyes now. Breathe deeply. Feel the vast, invisible architecture of existence gently supporting your rest.